Touch your desk. You feel the solid wood, right? You feel it's really there, fixed, unchanging. Richard Feynman would say you're experiencing an illusion, and quantum mechanics proves it. The reality you feel so certain about is, in fact, fundamentally uncertain. And I'm going to show you why. Think about the world around you. The chair you're sitting in right now. The screen you're staring at. Your hands. Everything feels solid. Everything's exactly where it should be. No weirdness here, right? Your chair isn't sitting in two places at once. Your desk doesn't vanish the moment you look away. This is the macroscopic world. The world we actually live in. The world that feels absolutely real. For centuries, physicists thought this solidity, this certainty, had to be reality's foundation. Newton built his entire classical physics on this assumption. Objects have definite positions, definite velocities. Know the starting conditions, and you can predict exactly what comes next. It's all deterministic. It's all locked in. It's how the world feels to us. But then quantum mechanics arrived, and it tore everything apart. Here's the problem. Everything around you, everything that feels solid and unchanging, is made of particles, atoms, electrons, protons. And when physicists actually looked at these particles, they found something mind-bending. They don't act like solid objects, not even close. They act like probability waves, in superposition, existing in multiple states simultaneously. Let me show you the experiment that proved this. It's called the double-slit experiment. And honestly, it might be the most important experiment in all of physics. First, imagine firing bullets through two slits in a wall. On the other side, a detector shows where they land. What do you get? Two bands. Exactly what you'd expect. Bullets go through one slit or the other. Old-fashioned particle behavior. Easy. Now try water waves instead. Waves pass through both slits. They meet up on the other side. They interfere with each other. Crests pile up. Troughs cancel out crests. And you see an interference pattern. Multiple bands. Not just two. That's wave behavior. Also straightforward. Third, try electrons. An electron gun. Two slits. A detector. What do you see? This is where it gets weird. You get an interference pattern. Exactly like the water waves. Multiple bands. Which means each electron is somehow passing through both slits at the same time. It's acting like a wave. Let that sink in. Think about what it means. An electron-1 particle isn't in just one slit or the other. It's in superposition. It exists in multiple states at once until the moment it's observed. Now, slow it down. Fire electrons one at a time, so slowly that only one electron is in the system at any given moment. Surely now you'd see the two-band pattern, right? Each individual electron has to go through one slit or the other. Nope. Look at the detector screen. Watch where the electrons land. Over time, the same interference pattern builds up. Multiple bands. Each individual electron is somehow interfering with itself, going through both slits at once. This isn't some abstract theory. This is what actually happens. But here's the really unsettling part. Now stick a detector at one slit. Measure which slit the electron goes through. Just watch it. What happens? The interference pattern vanishes. Just gone. Now you get only two bands. Pure particle behavior. The act of watching changed how the electron behaves. When you're not looking, it acts like a wave. When you watch it, it acts like a particle. That's not a lab mistake. That's quantum mechanics working exactly as it does. Measurement matters. Observation matters. Reality at the quantum level doesn't have a definite state until someone looks at it. Feynman, who won the Nobel Prize for his quantum mechanics work, was refreshingly blunt about this. He said nobody really understands quantum mechanics. Not the way we'd want to. But he could explain how it works. And here's it. What we observe isn't nature itself, but nature exposed to our way of questioning. Sit with that for a second. Nature exposed to our method of questioning. That's not just pretty words. It's a massive statement about reality. It means there's no objective reality out there separate from observation. Observation itself creates the reality we experience. And this is where we hit the core paradox, the one Feynman spent his whole career wrestling with. If particles are probability waves until measured, if observation creates reality, then why don't you feel like a probability wave? Why isn't your chair existing in multiple places at once? Why does reality feel so locked down, so predictable, so genuinely real? You're made of quantum particles, literally trillions upon trillions of them. Every electron in your body, every proton, every neutron, they all follow quantum rules. They're all probability waves, so why don't you feel it? Why doesn't quantum uncertainty define your own existence? That's the question. And it cuts deep. Because if quantum mechanics is real, and it is, no question, experiments prove it over and over, then the solidity you feel, the certainty in your experience, the reality that looks so solid must be either an illusion, or at least an interpretation. Your brain's way of processing something way more bizarre underneath. Feynman confronted this problem head-on. He didn't shy away from the weirdness. He dove into it. And his answer, the answer he developed over decades of work in quantum mechanics, is more radical than you might think. But before we get to Feynman's solution, you need to know what the measurement problem actually is. Why does watching something change how it behaves? What counts as a measurement anyway? Does it need consciousness? Does it need a human eyeball? A lot of people think yes. They figure consciousness collapses the wave function, that the human mind has some special power in creating reality. It's tempting to believe. It puts us humans back at the center of everything. But Feynman wasn't buying it, and neither does modern physics, because experiments show something different. Detectors measure things without being conscious. Particles choose their behavior even when nobody's watching. Measurement doesn't need consciousness. It needs information. That distinction, information versus consciousness, is huge. And it's where Feynman's answer kicks in. If measurement creates reality, but measurement doesn't need consciousness, then what is a measurement exactly? What's actually making the reality we feel? Go back to the double slit experiment. Put a detector at one slit and the interference pattern vanishes. But why? What's different? The detector isn't watching in any conscious way. It has no mind, no will. It's just a physical gadget recording information. Information. That's the key word. The moment information exists about which path the electron took, which slit it went through, the superposition collapses. The probability wave becomes a solid particle. It's not consciousness doing it, it's information. But that opens an even bigger question. If information collapses the wave function, if information makes reality real, then where's all that information about you? About your chair? About the macroscopic world that feels so solid? I mean, if electrons in your body are constantly in quantum superposition, if matter is fundamentally probabilistic, there has to be constant measurement happening, constant information being created. Otherwise, you'd feel like a probability cloud. You'd feel spread out. And this is where Feynman's answer gets fascinating, because he figured out that the environment is always measuring you. Air molecules banging into you, photons bouncing off you, quantum fields interacting with your body. Every single one of those interactions makes information. Every one collapses quantum superpositions. It's called decoherence. And for objects your size, it happens blindingly fast. About 10^20 seconds. A billionth of a second. Your quantum superpositions collapse. All the time. Non-stop. The environment measures you trillions of times every single second. So you never stay in superposition long enough to notice. You never feel quantum uncertainty, because it collapses instantly from environmental interaction. Reality feels locked down because it's being measured all the time. But that doesn't fully solve it either, because it just pushes the problem one step back. If the environment measures you, then what measures the environment? If everything is made of quantum particles, how do you ever get a solid reality in the first place? This is what Feynman dug into hard, and his solution means rethinking what reality even means. Because Feynman understood there's no hidden layer underneath measurement, there's no true reality independent of observation. What you measure is all that exists. Observation doesn't uncover some pre-existing reality. It creates the only reality there is. That's the uncomfortable truth at the core of quantum mechanics. And that's why reality feels real. Because measurement is reality. So if measurement creates reality, but it doesn't need consciousness, just information, then what counts as information exactly? When do you have enough information to collapse a superposition? What does that mean for what existence fundamentally is? Feynman spent decades wrestling with these questions. And his answer, built through his path integral formulation of quantum mechanics, is way more radical and beautiful than you'd expect. Because it shows reality isn't some fixed object we're looking at. It's a process. A constant cycle of measurement, collapse, and creation. But to really get it, to see why Feynman's answer blows everything open, you need to understand what he meant by nature exposed to our method of questioning. Because that phrase, so simple sounding, holds a complete revolution in how we think about reality. Feynman's path integral formulation. Let me break this down, because this is where his answer becomes genuinely radical. In standard quantum mechanics, you calculate particle behavior by tracking how they change over time through equations. Schrödinger's wave equation, Heisenberg's uncertainty principle, all that math. But Feynman thought differently. He asked, what if we looked at this in a totally different way? What if, instead of tracking one path, we imagined the particle taking every possible path at the same time? Picture an electron traveling from point A to point B. In regular physics, it takes one path. A straight line maybe, or some curve if forces push it. But in Feynman's way, that electron doesn't take just one path. It takes every possible path. It goes straight. It curves around. It goes up, down, loops, zigzags. Every wild, impossible trajectory you can picture, the particle does it, all simultaneously, in superposition. Now here's where it gets beautiful. Each path has a probability amplitude attached to it. When you add up all those amplitudes, almost all the insane paths wipe each other out. What's left are the most likely paths, the ones you see in regular reality. But this is the key. Until you actually do that sum, until you look at the particle, all those paths are actually happening. The particle exists in a superposition of histories. So what counts as an observation? What adds up those paths and picks one history out of infinite possibilities? This is where people usually get tripped up. The obvious answer, the one that seems right, is consciousness. Maybe it's your brain, your conscious observation collapsing the wave function. Maybe reality needs a mind watching it before it can become real. It sounds good. It puts humans, consciousness, right back at the center. It makes you feel significant, special, like your observation really matters deep down. And to be honest, some brilliant physicists seriously considered it. Eugene Wigner, a Nobel winner, suggested consciousness might affect wave function collapse. Hugh Everett's many worlds interpretation tries to sidestep the collapse issue entirely by saying, all possibilities happen, just in different universes. And there are weirder interpretations too, different versions of quantum mechanics that try to work consciousness in somehow. But here's the catch. Feynman wasn't convinced, and most physicists aren't either. Because there's a massive problem with the idea that consciousness collapses wave functions. It's simple. Detectors, machines, objects with no consciousness that measure things. Remember the double-slit experiment. Put a detector at the slits to see which one the electron goes through, and the interference pattern vanishes. But that detector isn't conscious. It's just some metal, electronics, maybe a photodiode that catches an electron passing by. It has no awareness, no subjective experience, and yet its presence shifts the outcome. The wave function collapses. The superposition stops. This isn't guesswork. It's been proven experimentally thousands and thousands of times. You can run the double-slit experiment with electrons, photons, even molecules. And every time, if a detector records information about which path the particle took, the interference pattern evaporates, even if nobody ever sees the data, even if the data gets erased later. The fact that the information exists somewhere is enough. That tells you something huge. It's not consciousness that matters, it's information. So what is information? In physics, information isn't some abstract concept. It's physical, real. You can touch it. When an electron hits a detector, it leaves a mark, a shift in the detector's state. Maybe electrons move, maybe an atom gets ionized, maybe a photon shoots out. Anything. It's all a physical change. And that change is information. It's proof that something occurred. And here's Feynman's key point. Once that information exists anywhere in the universe, the wave function collapses, superposition ends, the particle picks which path it went. Not because some mind saw it, but because information about its movement got recorded in the physical state of the universe. Think about it. When you watch something, what are you actually doing? You're interacting with it. Photons bounce off the object and hit your eyes. Those photons carry information. When they smash into your retina, they change it. They ionize molecules, fire up nerve cells, send signals to your brain. The whole chain is physical. And at every single step, information is being made, stored in the physical state of the universe. Your consciousness, your subjective experience of seeing the thing, happens at the end of that chain. But the wave function collapse. That happened earlier, the moment the photons touched the object, the moment information got created. That's why detectors work. That's why the double-slit experiment shifts when you add a detector at the slits. Not because the detector is aware, but because it makes information. It logs which path the electron took. And the moment that information exists, the superposition ends. The wave function collapses. The particle picks a path. Feynman said it perfectly. What we observe is not nature itself, but nature exposed to our method of questioning. Look at his exact words. Exposed to our method of questioning. Not exposed to our consciousness, not exposed to our minds, but to our way of questioning, to the tools we pick, to the interactions we set up, to the information we make. Reality isn't some fixed thing just waiting to be found. It's a process of interaction, measurement, making information. And what you see as reality is what comes from that process. Not the thing itself, but the thing as it shows up to your way of investigating it. Now think about what this means for your day-to-day life, because this is where it gets seriously weird. If measurement creates reality and measurement doesn't need consciousness, just information, then measurements happen all the time, without stopping, everywhere. Right now, as you're sitting here, air molecules are slamming into you. Photons bounce off you. The floor pushes you up. Every single one of those interactions is a measurement. Everyone makes information. And everyone collapses some tiny piece of your quantum wave function. It's called decoherence. It's what happens when quantum systems, through non-stop interaction with everything around them, lose their quantum properties and start acting classical. And it's fast. For something your size, decoherence takes about 10 to the minus 20 seconds. A billionth of a second. So incredibly fast that you could never experience being in superposition. The second you exist, you're already interacting with your surroundings. You're already being measured. You've already collapsed. And that's why reality looks solid. Not because it's basically solid, but because it's getting measured all the time. Always interacting. Always collapsing from superposition into certainty. And here's the profoundly deep part. Feynman understood you can't pull apart the observer from what's being observed. You can't point at out there reality and say, that's the real thing, separate from me. Because the second you touch it, the second you measure it, you shift it. You make information about it, and that information changes what you experience. Look back at the path integral formulation. The particle goes down every possible path. But when you measure it, when you make information about which path it took, you pick one history out of infinite options. And that history, that exact trajectory, becomes the reality you actually experience. But, and this is huge, that history didn't exist before you measured it. It wasn't sitting there, hidden, waiting to be uncovered. It was made by the act of measuring, by the information you produced. That's what Feynman meant by nature as exposed to our method of questioning. Nature doesn't have a definite state apart from how you question it. What you ask decides what you get. The tool you use to measure shapes the reality you end up measuring. It's not that reality is subjective, mind you. It's not like you can reshape it however you want just by thinking. Information is objective. If a detector records that an electron went through the left slit, it went through the left slit. Anyone checking the detector's data gets the same answer. Reality is objective that way. But here's the twist. Which slit the electron went through only becomes a real question. A real property of the electron when you measure. Before the measurement, before information gets made, the question has no answer. Not because you don't know the answer, but because there is no answer yet. The electron didn't go through one slit, it went through both. And neither. It lived in a superposition of possibilities. And only when you measured, when you made information, did one of those possibilities become actual. Think about what that implies. It means reality. The real, deep-down reality isn't made of things with set properties. It's made of possibilities, potentials, and measurement, making information, is what transforms potential into actual. Feynman spent decades working through these ideas, building the math, testing them with experiments, and the math works, flawlessly. The path integral formulation predicts experiment results with mind-blowing precision. It's one of the best tools in modern physics. And it's built on this wild idea that reality is a process, not a thing. But get this. If measurement creates reality, and measurement happens constantly everywhere in the universe, then reality is constantly being made. Every instant, every interaction, every bit of information made means some tiny piece of the universe collapses from possibility into reality. You're not just passively watching a fixed universe. You're a player in an ongoing creative process. Every observation you make, every interaction you have, makes information. And that information shapes the reality you see. You're feeling that reality is solid, fixed, predictable. It's an illusion. An illusion because measurement happens so fast, so constantly, that you never feel the underlying quantum weirdness. You only experience the collapsed outcome. The regular, predictable universe your brain evolved to understand. But under that illusion, at the deepest level, reality is strange. Probabilistic, built from possibilities. And your observation, your measurement, the information you create, that's what makes one of those possibilities real. Feynman always said nobody truly understands quantum mechanics, and he was right, because it destroys every gut feeling you have about how reality ought to work. But the math works. Experiments back it up. And the picture it paints is so weird, so stunning, so fundamentally disturbing, that it shifts how you see everything. Because if measurement creates reality, then what is reality? Is it a solid, objective thing separate from you? Or is it an ongoing cycle, shaped by the questions you pose, by the interactions you have, by the information you produce? Feynman say it's the second one. And if he's right, if nature really is exposed to how we question it, then your experience of reality isn't a passive window into a fixed world. It's you actively creating that world. Every observation counts. Every measurement determines what's real. And you're feeling that reality is locked down. That's just your brain making sense of trillions of measurements happening every second, collapsing the quantum universe into a regular experience you can move through. But that opens an even deeper question. If measurement happens constantly, if information keeps getting made, why does your reality feel so stable? Why don't you sense yourself jumping out of superposition constantly? Why does your experience feel so locked in, so regular, when the underlying physics is totally probabilistic? The answer's simpler than you'd guess. And more disturbing. It comes down to scale and speed. Picture it like this. Every measurement counts. Every observation collapses a superposition. True. But there's something Feynman caught on to that most people totally miss. You're not alone. You're surrounded. Every single second, every fraction of a second, every split-second fragment, you're being measured. Not by people, not by machines, but by everything around you. Air molecules, light photons, dust particles, heat radiation. All of it interacts with you. And every interaction counts as a measurement. Every photon bouncing off your skin is measuring where you are. Every air molecule hitting you measures how you're moving. That's called environmental decoherence. And it's why you never feel like a quantum superposition. To feel quantum superposition, to experience reality as probabilistic, you'd need total isolation. No light, no air, nothing interacting with you, complete isolation. But that can't happen. Even in empty space, heat radiation exists. Even at near absolute zero, fake particles flash in and out. The universe keeps measuring you. And here's the scary part. For big objects, things your size, a chair, even a speck of sand, decoherence happens insanely fast. How fast? 10 to the minus 20 seconds, 0.1 seconds. That's the time it takes for the environment to collapse your quantum state. That's how fast you go from superposition to a set state. You never stay in superposition long enough to catch it. Ever. The environment measures constantly. It's unstoppable. It's so quick your consciousness never gets close to that quantum moment. That's what Feynman meant by the classical limit. Quantum mechanics doesn't vanish at big scales. It's still there. It's still the foundation. But its weird effects, its uncertainties, its randomness, all that gets buried under trillions of measurements every second. And there's one more reason reality feels so predictable. Size. Like this. A single electron is probabilistic. Its spot is fuzzy. Its momentum is fuzzy. It's a probability cloud until measured. But you're not an electron. You're about 10 or 28 atoms. Roughly 10,000 quadrillion quantum particles. And when you've got so many particles, something cool happens. Individual uncertainties balance out. Picture a forest. Up close, trees are all different. Some tilt left, some right. Some tall, some short. Step back and look at the whole thing and it seems uniform. Differences cancel. Same thing happens with quantum mechanics at big scales. Each particle is uncertain, but with trillions working in tandem, uncertainties wipe out. Collective behavior gets regular, gets predictable. That's the classical limit physicists talk about, where quantum mechanics shifts to regular Newton physics. Not because rules shift, but because so many particles exist that quantum wiggles don't matter statistically. Your chair feels solid because trillions of atoms act together, and their individual quantum uncertainties average out, building the sense of solidity. You feel regular because trillions of particles in your body get constantly measured by the environment, collapsing their randomness into solid certainties. Stop here. Let that soak in. Your feeling of reality, that gut experience that you're solid, the world is steady, things are predictable. It's not quite an illusion, but it's not ground truth either. It's an understanding. Your brain evolved to move through the big-scale world. It learned to interpret endless measurements. It learned to spot patterns, assume things continue, feel the world as regular. But deep down, reality's still random, still quantum, still bizarre. Feynman said it in a way that was stunning and unsettling at once. He said what we see isn't nature by itself, but nature as it shows up to how we question it. Chew on that. There's no reality separate from measurement. No hidden real state underneath what we see. What you measure is what exists. Reality has zero fixed shape until you ask. And your question, how you measure, shapes the answer you get. It doesn't mean reality is subjective, like you can dream things into being. No. Quantum mechanics has laws, has math, has patterns. But it does mean reality isn't separate from whoever's looking. It's not a dead stage where stuff occurs. It's a living back and forth between quantum stuff and how we check it. And here's the hard truth Feynman completely accepted. You're not just watching reality, you're creating it. Every moment your eyes soak up photons, you're collapsing wave functions. Every moment your skin senses pressure, you're measuring quantum positions. Every moment your brain takes in information, you're bringing together billions of quantum measurements into one experience. Your consciousness doesn't make reality, but the information floating around about reality, the measurement happening between you and your surroundings. That's what makes reality solid. That's why reality feels real, because you're constantly measuring it. And measurement makes things real. There's no layer hiding underneath. No true reality sitting there waiting. What is what can be measured. And what can be measured depends on how you ask. Feynman worked on this for years, and he reached a conclusion most physicists hate to swallow. But it's mathematically unavoidable. Reality is relational. No absolute location, just location relative to other stuff. No absolute time, just time relative to someone watching. No absolute quantum state, just state relative to information about it. So your feel of reality, that sense that things are locked down, and sure, it's real to you. It's legit. But it's not universal. It's specific to your viewpoint. Picture it. Two observers measure the same quantum system and get different answers. Not because one's wrong, but because reality differs from their perspectives. The information each one has access to is different, and information sets what's real. This isn't just thinking out loud. This is actual physics. This is mathematically proven by quantum mechanics. And that's what Feynman meant when he said nobody truly gets quantum mechanics. Because really getting it means accepting that reality's not what you picture. It's not a world of hard things moving through space and time. It's a world of options turning into facts whenever information pops up. And you, with your brain and senses and non-stop measuring, are actively part of that transformation. So why does reality feel so real? Because you're constantly measuring it. Because your environment's constantly measuring it. Because trillions of measurements each second create the illusion of smoothness and predictability. Because your brain learned to see that info as a steady, regular world. But under that experience, the real truth is way weirder. Reality is random. Reality is relational. Reality gets made through measurement. And you're not just a bystander. You're actively part of it. Every question you ask gets the answer shaped by how you ask. Every measurement you make turns a possibility into a fact. Every moment of consciousness is your brain bringing together results from countless quantum exchanges. Feynman grasped this, and he never tried to smooth it over. Never hid the weirdness, leaned into it. Because the real story about reality isn't that it's easy. It's that it's crazy, gorgeous, impossible to reduce further. And that craziness is exactly what makes it so unbelievably awesome. Next time you touch a desk, you sense solidity. But what's happening is trillions of atoms in your finger electrically pushing away trillions of atoms in the desk. That push, that force, comes from ghost photons zipping in and out of being in split seconds. You never touch anything real. You only feel electric fields colliding. And that colliding counts as measurement. And measurement collapses quantum states. And those collapsed states build the touch you feel. Reality feels real because you're inside it. Because you're always measuring. Because measuring makes things real. Now you get what Feynman got. That reality's not how it looks. That watching matters. That information is base level. That you actively build the world you go through. That doesn't make reality less real. It makes it weirder, more interesting, more awe-inspiring. Because hidden under what you see, touch, taste, there's a quantum world of endless possibilities. And by measuring, by watching, by taking part, you're constantly turning possibilities into realities. Reality feels real because you're making it real. All the time, every check, every look. That's Feynman's solution to the question we began with. Why does reality feel real? Because measurement makes things real. And you're forever measuring. The universe doesn't stay hidden. It shows itself to those asking smart questions. And now you know how to ask those questions. The world won't ever feel quite the same. Share this with somebody who thinks reality's simple. Tell us in the comments how Feynman's answer lands for you. Happy? Or way more curious? Because if Feynman taught us anything, it's that great answers always birth harder questions. And harder questions, those are worth your time.